Show in a picture using component triangles that it makes sense if two vectors are added. It's the same as just adding the components. So I've said on the key concepts page that if you have the vector C is equal to the vector A plus vector B, that means that that holds true for all the components as well. But how do we know that that is true? That's kind of what this example is about, is can we do some, draw a picture, do some geometry to demonstrate that it's true. And this is kind of following my concepts first maybe approach to vectors. I mean, I think if you looked up in a math class, how would you prove something like this is true? It might be a little bit different. But, let's, in that sense, let's say I've got vector A here, and then maybe I'm adding head to tail to that another vector. Let's say I'm just going to have some other vector, and this is going to be vector B. So here's vector A, here's vector B, and in that sense the two components would be like this, right? Here would be the x component, that would be A sub x, here's A sub y. The B I could also break into components, B sub x, and here's the vertical component B sub y. And if I look at kind of I didn't really draw the full resultant vector in here, but if I looked at the components of the resultant vector, I'm going to draw it a little bit here's maybe the horizontal component, and then there'd also be a vertical component. I'm going to draw them spaced a little bit separately. But if you think about vector C, right, wouldn't vector C kind of be right there? And this would really be C sub x, and this would be C sub y. And I think it kind of makes sense that the segments AX and BX really comprise together, if you put them end to end, would be the length of CX. And similarly for the vertical, if you move this AY kind of over here and just stack them together, you get the length of C sub y. And so I think that kind of geometry demonstrates that these two component equations are correct. Let's check that in the slide here, because I think the slide is going to actually do a similar thing, maybe a slightly different set of vectors, but it didn't really name them because in the question I didn't put names, but there's the first vector with its two components. There's a second vector, and now its two components are coming in. And then if we look at that component and that component, those are really the two components of the resultant vector, the one that I represented with C here on my whiteboard. But again, demonstrating that what I'm saying is correct. And then I'm not going to go and demonstrate that this is true for other kinds of equations, but it turns out you could kind of build upon what is being presented here to show that it works for those other kinds of equations that we'll be looking at.